Okay, and off we go. So, make sure to get that attendance quiz, score entered, details, etc. Okay. Off we go into the math. So last time, we were talking about multivariable functions. There's a bunch of little micro details in there that again I suggested that y'all can read on your own. You know, technically, what is the domain and what does it mean for a function to be injective and little stuff like that. Okay. All right. So off we go. We're going to talk about how to visualize multivariable functions. Y'all have seen graphs before. This is technically the definition, if we want to get real precise about what we mean by the graph of a function. I think that's a little hard to work with. It's sort of clunky notation. We don't really need that for our purposes, so I'm going to kind of show you by examples. Okay, so this is what you're already very familiar with, I assume. This is the graph of a single variable function, and let me walk you through the obvious, right? But for the purpose of setting up the analogy that we will extend to the higher dimensional set in just a moment, right? So that different ways to think about this, but you could think of it as, well, for every input point, for every input value from the domain, you use the formula to compute the corresponding output value in the target. And then those give you, between the two of them, those give you the coordinates of a point x comma y. X is the input, y is the output. We kind of smash those. I mean, these are not, it's a little weird if you think about it. These points, the x and y, don't even come from the same space. Right? One's from the domains, one's from the target. But we're going to smash those coordinates together to make the coordinates of a point now in 2 dimensions. Again, let me just point out the obvious but nevertheless weird aspect of this. We're drawing a picture in 2 dimensions. R2 is not the domain. R2 is not the target. We made up the XY plane. We made it up, right, for our purposes to be able to draw this picture. So the idea is then that the graph is the collection of all points that you can create in that manner. Okay. Now that's one way to think about the graph. Here's a kind of, I don't know, there's a couple of different ways that you could think about it. You can kind of think about the domain being the x-axis. It's a little bit of a math crime. Technically R1 doesn't live inside of R2. Right, but anyway, that little stickler point aside, if you think of the x-axis as being the domain, after all, that's where the x's come from, you can think of the formula for the function telling you at every point how far should you sort of push upward to get to the graph. That's another way to think about it. And here's another way to think about it. And all of these are useful at different times. Another nice way to think about it. The graph is what you get when you set the output values of the function equal to a new variable. So we started off with this function called f. F is defined in terms of input. Let's say we call the inputs x, right? And you give me an x, out comes f of x, end of story. Notice there was no y in the discussion of what the function is, right? We are making the choice. It is part of the graph construction that we choose to label these output values f of x as being called by the name of another new variable that we create. In this case, we're going to use y. Right, so I like to, again, pithy summary. The graph's what you get when you set the output values equal to a new variable. Excuse me, in this case called y. Okay, let's do all the same stuff over again. Now, for a multivariable function, now we have a 2-dimensional domain. You can think of the 2-dimensional domain as kind of being the xy plane down here in space now. right? You can think of such an input point, now a two-dimensional point, x comma y. Both input coordinates. Right? You list those first, and then you plug into the function, see what you get. You get some output value that'll be in the target. That output value you then list second, and then then all together with the inputs and outputs. And again, weird, right? Domain and the target are different points, completely different things. These come from the domain, these come from the target. But when you smash them together, you get a point in 3 dimensions, and then you can plot that point in 3 dimensions. So it's totally analogous. Right? It's kind of a rip-off of what we did for the single variable graph. Right? But now the dimensions are different because we have multiple input variables. Okay, and then again, you can think of this in a couple different ways. You can think of this as the formula for the function tells you how far to push up from the, again, forgive me, what you think of as being the domain down here, namely the XY plane. I think this is a useful point of view, if nothing else, for the fact that it helps me understand how the graph is two-dimensional. Right? So we get a surface. We get a two-dimensional surface because we're taking the domain, which is literally two-dimensional plane, right? The definition of two-dimensional, right? And we're just kind of all the points in that two-dimensional thing, we're just kind of shoving them upward by different amounts. No surprise, would generically expect to get a two-dimensional surface. Okay, and then, again, also useful in its different ways. Another way to think about this, you give me a function. The graph is what you get when you set the output values equal to a new variable. Again, f was defined in terms of variables x and y. The output value is called f of x comma y. Period. Right? End of conversation, really, in general. We choose, as part of the graph construction, to give a name to the output variable, calling it z. You don't have to do that, right? That's part of the choice of using the graph construction. All right. Okay, so that's pretty much how graphs work. They're useful. No surprise, right? If you think back to Calc 1, Calc 2, it's all single, everything you did before single variable calculus, pretty much every picture you draw is like that, right? Every picture you drew of a function previously is probably a graph following these rules. So hopefully that all seems pretty familiar. I do want to emphasize that just because it satisfied our every need up to this point doesn't mean that it's going to satisfy all of our needs going forward. And in fact, it's not. We're going to find a really nasty problem, a real shortcoming of the graph construction that's going to really limit how much good we can get out of this. And the shortcoming is pretty easy to notice. Let's try to do this for a function of now 3 variables. You can probably see where this is going to go, right? If you've got 3 input variables, and then you introduce another output variable, altogether you now have 4 variables. That means the graph consists of a bunch of points that live in 4 dimensions. We can't draw it. Right? Crash and burn. This doesn't work. Doesn't make any sense. I don't know. I can't. We're mere 3-dimensional critters. We don't know how to draw in 4 dimensions. Does everybody see the problem there? Okay, so the good old days of single variable calculus, where it's perfect for single variable calculus. In a single variable setting, the graph lives in 2 dimensions, and we have 2-dimensional paper. Right? The graph itself is a 1-dimensional thing because it comes from a 1-dimensional domain, and we have pencils that make one-dimensional curves. It's perfect. It's a match made in heaven, right, for single variable calculus. So graphs are awesome for single variable calculus. They're, doable, I guess, right? When you have a second input variable. And that's it, right? Everything beyond that, you're out of business. So the upshot is we're going to have to think of other ways, different ways, not graphs, different ways to draw pictures of functions, right? The graph construction just isn't gonna do it. So along those lines, you got to make really, really careful about this point right here. It's very common in before you get to multivariable calculus. It's very common to talk about a graph as if it is the function itself, or to talk about the function, talk about the shape of the function, the function is concave up, stuff like this, where we're conflating the function itself with the graph of the function. And in single variable calculus, you can get away with that. In multivariable calculus, it's a really bad idea, because the graph is a particular construction, shortcomings and all. The function itself we're going to represent with various different constructions. Is everybody with me? Does that all kind of make sense? Okay. All right. Oh, but related note. Very commonly, my experience has been that students at this level often also kind of use the word graph as kind of a catch-all term to describe any picture. And again, in single variable calculus, you can get away with that in most cases. Who cares? It just kind of works. It's fine. In this situation, you really can't do that either, right? So if you are looking at a picture, you want to describe that picture, don't call it a graph unless you are saying that it literally is a graph per this exact construction. Otherwise, it doesn't make any sense. Okay. All right. Let's talk about some other types of pictures. This is one of my favorites, actually. And very common kind of a picture to draw. Very natural in a lot of ways, and I've seen it a million times in a million books, and I've never seen a name attributed to this picture. I think it's because it's so natural. And so I'm going to, just to have a name to call it, I'm going to call this the literal picture, because I make the case this is kind of what this picture is. We've got a function. We're going to draw a picture indicating this function by, okay, there's the domain. Okay, I'm going to literally draw the domain. Domain's R3. Boom, there's R3. The function has a target, R1. Okay, there you go. R1. I'm literally drawing the target. What does the function do? Well, the function takes points out of the domain and puts their images in to the target. And so I'm literally going to draw an indication of sorts here anyway, that's what the function's doing. It's taking points out of here and dropping their images in over here. It's a pretty literal picture of what the function is and what the function does. Okay, now that said, pretty disappointing, right? Let's talk about things we like about the graph. Why do we like the graph? Oh, well, golly. I mean, you look at pictures like this. How the graph is sloped tells you about the calculus of the function, namely tells you about the derivative. The concavity, whether it's concave up or concave down, tells you about the second derivative. There's very strong relationships between the geometry of the picture and the calculus of the function that the picture represents. That's fantastic. Gotta love it. Where's the picture? Where's the shape? I don't see any curves. I don't see any concavity. I don't see any slopes. I got nothing. Right? So it's pretty disappointing. You may be thinking to yourself, you know what? I like graphs better than this because of that reason. Let me just point out, though, let's compare apples and apples. I did an unfair comparison. I compared the literal picture of a function of 3 variables with the graph of a function of only 1 variable. The fair comparison would be to compare this picture, however disappointing it may be, with the picture we get for a graph of a function of 3 variables, which of course, we got nothing. Right, so which is better? Absolutely nothing or disappointment? I think you got to go with disappointment, right? All right. Okay, now that said, this is more useful than what I've depicted here so far. Let me show you a situation where this is actually really natural thing to talk about. If I have a point here in the domain, let's call it A, I guess. Right, and I look at its resulting image there, f of A. Fine. I like to, I don't know why, but it just, I like the sort of the construction, the metaphor of, I like to think of that's where I am, right? So that's me right there, right? So I'm at this point. While I'm at this point, the function has this value. What would happen if I started to move in some direction? Well, we would represent movement by way of a vector in the domain, because of course I'm in the domain, I'm moving within the domain, so we get a vector in the domain. Let me call that V. Right? And, well, hopefully not a big surprise, if I'm at this point and I start to move, if we change the point that we're plugging into this function, no surprise, the image will also start to move. I don't know how, I don't know which way, I don't know how fast, right? But it'll start to move in some sense. And so arbitrarily, let me just draw, for example, that's supposed, oh gosh, that's terrible. Let me try that again. There we go. It'll move with some velocity, and I can represent that movement, again, by an arrow. Now, how do I figure out what that arrow, or what this velocity is? You know, given where I am, given the velocity that I'm moving with in the domain, how would I find the resulting velocity in the target? It's a separate thing. We'll talk. It's going to take us a bit to work up to that. Not that big of a deal ultimately, but that's a separate question. My point here is that notice how the question that I've described is very naturally represented on this literal picture. Really makes sense. Here's the inputs, here's the outputs. Here's how the inputs move. I want to know how the outputs move. Everything's natural. So what we do with this and how we're going to solve the question, again, you know, it'll take some time, but this is a reasonable way to at least entertain what the question is. All right. Okay, let's talk about another one, level sets. Again, we have a bunch of sort of formality here. I'll talk through that in a second. I think it's kind of easier to get the ball rolling by just looking at an example. So here we go. Got a multivariable function here. You'll notice what I've drawn here is the literal picture. Got the domain on the left, 2 dimensions because there's 2 input variables. So domain on the left, target on the right. And the way we form a level set is we start by picking a point on the right. We pick an output value, and then we ask, what are the corresponding input points that the function would take to that selected output point? All right, so let's actually do it. Excuse me. Let's see here. Well, I'll tell you what. Let's go up to the definition here, and let's kind of walk through how this makes sense out of the definition. Given an output point, oh, you know what? I'll go into the highlighter mode. How about this? Given an output value, the level set for that output value is going to be the collection of all of the corresponding input points that when you plug them into the function, give you exactly that selected output point. Said differently, we're going to take this output point, we're going to set the function equal to that output value, and then we're going to solve for what are the corresponding input points. And I think you can persuade yourself, doesn't take too much trouble. If you set this function x squared plus y squared, so f of x, right? If you set that equal to our selected output value 1, you get the equation x squared plus y squared is 1. We all recognize that. That's the unit circle. So this over here then, these points on the unit circle, that's our corresponding level set. Everybody happy with that? Okay. So the definition up here, you can kind of see where, how that's just representing the process that we're describing down here. By the way, let's talk about this notation, this F inverse notation. How does that make sense? Why would I call it F inverse? This function might not even be invertible. This function here is definitely not invertible. It doesn't have an inverse. How can I talk about its inverse? Okay, so it's just not what this means. This is slightly sloppy, but very convenient and very common routine notation. This does not say find the inverse function of f and then plug in that point. It's just not what it says. This just says, given the output value, we're going to kind of move backwards from that output value, and I will point out that since we started with 1 and we ended up with this green set, you can see we're kind of moving backwards from the direction the function's going. So it's a little bit sloppy, but it's very common, it's very convenient, and ultimately kind of natural in that sense. Everybody buying it? Okay. Let's see here. All right. So given any output point, there's a corresponding level set. We could take a second output point. It has a corresponding level set. By the way, you can pick as many output points as you want. Draw correspondingly as many level sets as you want. Now, I'm going to make a gripe about this. I can't choose all of the output points. If I chose all of the outputs, I would get correspondingly all of the inputs, and the picture would just be a solid, like I would have drawn so many curves, the picture would just be a solid mess. Okay, so unavoidably then I'm going to have gaps. And I feel like that's disappointing. So the pictures that I'm drawing here, they tell me what's going on at this point. They tell me what's going on at that point. It tells me nothing about what's going on like in between them or outside of them or inside of them. I draw nothing in there. It's pretty disappointing, right? Now, to be fair, come back to the picture we drew of a graph here. And it's tempting to say, well, yeah, that's the graph, and that's got all of the information about the function. But what have I actually drawn? I've actually drawn very little, right? I've drawn these kind of edges as if, in the usual way, I'm sort of representing something. I'm trying to appeal to your imagination that I've got some sort of a curved surface like this, right? But I didn't draw anything in here either, right? So your imagination filled in the blanks. That doesn't really count, right? So I'm going to say that both of these kinds of, if you have a function of two variables, and that's what we were drawing a picture of the graph of here. This is a function of two variables. Let's see here. Let me. So this is a function of two variables. The graph is, in fact, kind of disappointing. It doesn't really tell you. You can't see everything. It just, you're going to have to use your imagination a little bit. And likewise with the level set here. Yeah, it leaves a little something to your imagination also. And I think that's kind of a push, frankly. Everybody with me? All right, so it's just another tool for your toolbox. So it's a different way to represent a function. Sometimes it's very, very convenient. Here's an example of how it can be really convenient. Anyone who's done any hiking is aware of this thing called a topographical map. And they tend to look vaguely kind of like this. I'll show you a real one in a second here. Oh, my shirt. Right? Some of you may have already noticed. Yeah. Which, by the way, I did not special order this. I just was walking through the store one day and I was like, oh my God, I gotta have that. Right? Anyway. So topographical map, the big idea is that every curve on a topographical map represents a constant altitude. So if it represents a constant altitude, what that means is it represents a constant value, a fixed constant value of the function that tells you altitude, namely the altitude function. You give me an x and a y. H tells you what is the altitude at ground level at that point. So it's a different way to think about contour lines and topographical maps. It's just giving you a bunch of different level sets of the altitude function. And I think this is fantastic intuition. When I look at a bunch of curves that are level sets of some function of two variables, honestly, even if altitude has nothing to do with the question and it's just a bunch of level sets of some arbitrary function, whatever, in my mind I'm always thinking altitude and contour lines and topographical maps. And if I were hiking in this direction, would that be uphill or downhill, and stuff like that. So really nice intuition. Okay. Yeah, sure. While we're at it, let me go ahead and show you this one. So this is a real topographical map. By the way, there's just endless supply of, I think, pretty cool topographical maps on. It's some government website. I think it might be USGS, something like that. I'm seeing some nods. So if you want to know what's going on in a certain area, a mountainous area, here's a map that gives you just a tremendous amount of information, right? So this, I picked this one because this is a peak that I climbed when I was in my youth. And there's the peak right there. Goes up to just under 13,400. A lot of work to get up there. So here's a couple of things that I can just point out pretty easily because of this map. First thing I'll point out, see how close the lines are together right here. Right, these various contour lines, okay, I guess they just call them contour lines. But anyway, level sets of the altitude function. Being close together, what that means is all of the altitude difference between any two contiguous lines, however much altitude that is, that altitude change happens over a very short horizontal distance, which means it's very steep, right? And I can attest personally, if you're standing right there, right next to this very steep area, you're going to notice because it's basically the edge of a cliff, right? And it's going to feel like you're looking straight down because, fear of heights, hopefully you have a healthy fear of heights, right? But anyway, I think in actuality it's about that steep. It's quite steep, right? But when you're up here looking down, it feels straight vertical. Yeah, by the way, if you were to not have a sufficiently healthy fear of heights, and if you were to, you would not stop falling for about 1,200 feet. And whatever is left of you would come to rest 1,200 feet lower. All right, so got to take that seriously. Here's another interesting thing you can see on the picture. Let me come down here. So earlier in the hike, you can see it. So the little dashed line there, this is the trail, and you can see it does what are called switchbacks. So rather than going straight up the side of the mountain, now it's not all that steep along in here, except that by the time you get to here, you've already climbed 2,000 feet, and by the way, you're at a high altitude and there's not as much oxygen, and trust me, you're going to find this pretty hard, right? Pretty challenging anyway. So doing this, what they call switchbacks move, instead of going straight up the mountain, which again, you would be covering, you'd be accomplishing, gaining altitude in the amount of however much these lines are separated by over very short distances. You go straight up the mountain. If you do it with switchbacks, then instead of gaining, I don't know, I think it's like 50 feet or something. Instead of gaining 50 feet over that short distance, you gain that same 50 feet over a greater distance. It makes it less brutal of a climb, right? So most hikers appreciate keeping it a little bit more level. You're still going to gain the same total amount of altitude. It's just a lot easier at less steepness. Okay, so anyway, nice information, right? If you're on a hike, we've seen some useful ways to make sense out of level sets, right? There is information to be gained from looking at level sets. It's not a graph. Different kind of a picture that we draw to understand a function. How are we doing that? Alrighty. Alright, so yeah, graphs and level sets are different. Now that said, they are related. Here's a cool little connection. We know that graph means you set the value of the function equal to a new variable. We know level set means we set the value of the function equal to a constant. The difference is one's a variable and one's a constant. And I make the observation that, well, if you were to set that new variable equal to that constant, in other words, if you write z equals c, notice what you're doing. Z equals c, that's a horizontal plane. You're basically taking a horizontal cross-section of the graph that you'd already constructed. So, yeah, you do get ultimately the same thing. If you set f equal to z and then z equal to c, that is kind of the same thing. It's just setting f equal to c in the first place. And the punchline then is that level curves, level sets in general, well, let's say level curves, are horizontal cross-sections of graphs. Rolls off the tongue pretty nicely when you say it like that. Now, I did just commit a little micro math crime. I'm going to confess to my crime in a couple seconds, but let's focus on what's right about this. This is, I'm going to say morally kind of correct. Level curves are horizontal cross-sections of graphs. Let's see it in action. Here's a function. The level sets are concentric circles around the origin, setting f equal to a constant. Let's look at the graph. The graph is what you get when you set it equal to this new variable z. Now I'm gonna ask you to trust me on this for the moment. We'll get around to the details of why this works in just a couple minutes, actually, time permitting. But this equation, x squared plus y squared equals z, for the moment, just take my word for it. It looks like this. It's kind of a bowl. Now again, cannot emphasize enough. These are clearly different. We're looking at the same function. It's the same f. We're understanding this f in two different ways. On the one hand, here are the level sets. On the other hand, here's the graph. Obviously different. They're totally different things. But, as promised above, if you take horizontal cross sections by setting z equal to c, right, here's those horizontal slices. Geometric appeal, if you take a horizontal slice of a bowl like that, you get circles, don't you? And in fact, asterisk, math crime, these circles are the same as those circles. Everybody see what we're doing? See how that makes sense, right? It's the same algebraically. It's just kind of a different way of getting to the same thing, and nice natural connection. So they're different constructions, but they're related by way of this cross-section thing. Yes?
Why is it that we have two C's? Or like...
Oh, I was just drawing a couple of different level sets. Yeah, so you can draw as many level sets as you want. I just chose two because I didn't want my picture to get too messed up, right? And then two cross sections correspondingly. Yeah. Okay. Now let me confess to the crime. What did I say that's wrong here? The actual level sets, you'll notice, live in 2 dimensions. A point on one of these level sets has 2 coordinates, x and y. That's it. Not so with these, right? So these circles, these are not, they don't live in 2 dimensions. They live in 3 dimensions. See? Right? We have an x, y, and a z axis. A point on one of these cross sections has 3 coordinates. So okay, it's a little bit wrong to say that they're the same thing. Obviously, what I mean when I say they're the same thing is that each one of these circles, the relationship between x and y, ignoring z, is the same as the relationship between x and y on the corresponding actual level set. So they're the same except for the fact that these are sort of elevated up in 3 dimensions, and these have never heard of 3 dimensions. So again, it's a little fussy. In most cases, we don't need to worry about this, but I just felt like that has to be pointed out. Everybody good? Okay. Yeah. So we've got various different constructions now for representing functions. If you give me a function, I can talk about the graph. I can talk about its level sets, etc. You can turn that around and say, let's suppose that I have a geometric object. I'm going to take a line, for example, this line right here. Come on. I can do better than that. That line right there. I can ask, is this line the graph of some function? And I can likewise ask, is this line a level set of some function? And then I can ask a third question, is this line the image of something? In other words, is there some function that will generate points on this line? Oh, wait a minute, we already talked about that. That's called a parameterization. So the answers to all 3 of those questions are yes. And here are the functions that do it, and I'll talk through some details about where these functions come from in a quick moment. But notice, very importantly, 3 different functions. Now, if you're sloppy about how you think about this kind of thing, then a question that would seem pending is, why are there 3 different functions? It's only one line. Right? Now, the answer to that question is because they relate to the line by way of completely different constructions. The line is what you get by applying the graph construction to this thing, by applying a level set construction, totally different construction, to this thing, and by looking at the image. It's not a level set, it's not a graph, right? But just looking at the image, the actual outputs from this function. So, yeah, 3 different functions because they relate to the line in 3 different ways. Does that make sense? Okay, now here's why I think that's important. And by the way, I've seen this. I've been teaching multivariable calculus for a long time at this point, and I've seen a lot of mistakes that students have made. And a really common mistake that I used to see more of, but I see less and less of the bigger a deal I make out of this, is for students to take what they know about how calculus looks on graphs. Right? Y'all know some calculus of graphs. You know, the derivative tells you the slope, and Second derivative tells you the concavity, and there's calculus. The algebra of the calculus tells you the geometry of the graph. That's why that's called the calculus of graphs. And I will see students apply the calculus of graphs to the wrong function, where it makes no sense. You can't apply the calculus of graphs if the thing you're interested in isn't a graph of that function. In this case, this function g, it's a level set of that. This is a level set of that function. It's not the graph of that function. So applying the calculus of graphs to a function whose graph isn't what you're interested in just doesn't make any sense. More immediately, the problem is that you will get garbage answers that don't make any sense. More importantly, your reasoning doesn't hold any water. It's just a bunch of nonsense. Does that make sense? Is everybody on board? You see the issue there? Now, the awkward thing about talking about this right now is that currently we don't know any calculus of level sets. And we don't currently know any calculus of parameterizations. Right? But we will. We'll know in a couple weeks. What I'm trying to get across now is make sure that you are very clear on the difference between the graph construction, the level set construction, and parameterizations. Because the way calculus looks in those three different contexts is completely different. Right? And you got to make sure to apply the right kind of calculus to the right kind of function to avoid, again, just producing nonsense. Everybody buying it? Okay, how do I get these functions? Let's talk about this. Okay, so the second one is actually the easy one. Let's start with a nice little layup here. How did I come up with this function? Keep in mind, I want to be able to talk about a level set of it. Wait a second, how do I make a level set? Okay, I make a level set by taking whatever the function is and setting it equal to a constant. So, I want to look at the given equation and I ask, what function, if I were to set it equal to a constant, would give me this equation? And it practically leaps off the page. Well, it's already written as some function being set equal to a constant. In other words, it's literally already written as a level set of a function. There it is. It's 2x plus 3y. Is that cool? Everybody happy with that one? Okay. By the way, if the algebra had not been sort of so convenient, if I had non-constant terms on both sides of the equation, whatever. Just take whatever you got on the right and subtract it over to the left, and now you've got what you need. Okay. All right, so that part's usually pretty straightforward. How did I get this function? Well, let me be more careful. How did I get this function? Okay, well, let's see here. I'm looking for something that, when I take the graph, I'm looking for something that when I set it equal to y, gives me this equation. It is not currently written as stuff equals y. Okay, so solve for y. Right? Once you solve for y in this equation, what you get is this. And now having rewritten it in this form, what is it that I have set equal to y? Well, this is what I have set equal to y. Yep.
For the level set, why does the 6 just kind of not matter?
Oh, well, because when you talk about level sets, you can take lots of different level sets for a given function. Yeah. So a given function has only one graph, but it has lots of different level sets. And so I arbitrarily chose, let's see here, let me get rid of all this. I just arbitrarily chose to, let's set this equal to 6, and then boom, we win. All right. By the way, I could have done the following. I could have said 2x plus 3y plus 1 equals 7. And that is just as good, right? So you can use any number of different actual functions just by choosing the appropriate constant on the other side. Yeah.
So we could have said 2x plus 3y minus 6 as your level set?
As well as the function whose level set is that. Yeah, so specifically 2x plus 3y minus 6 is a function for which the 0 level set is the line. That's right, absolutely. And by the way, feel free to get creative. There are some circumstances where fiddling around with the algebra in different ways can be useful, and you got a lot of flexibility a la this. Yeah. Okay, and how do we parameterize? Well, that's a chapter 1 thing. So we talked about that last week at some point, probably, or maybe the week before. Anyway, a while ago. And make sure you remember how that works. Side note: there are lots of different parameterizations for a line. You can pick any starting point you like, for example. Pick any vector parallel that you like. So this is not the only parameterization. This is just a parameterization. Okay, so careful with all of that, and we've already talked through all of that stuff. Okay, here's a neat trick. The trick here... Oh, you know what? I'm sorry. I got ahead of myself. I wanted to give y'all a warning about this. There are several old test questions that I'm sure y'all can find, right? All my old exams are on the website. Several old test questions that are basically this example. Different curve, whatever. It is very easy to underestimate questions like this. I've seen a lot of students underestimate these questions, right? The algebra is pretty easy, right? I mean, how did I come up with this function? I solved for y. Y'all could have done that in middle school, right? It's really easy algebra. That's not the point. The point to questions like this, why am I making a big deal out of all of this, is because it's really, really important to make the proper distinctions between graphs and level sets and parameterizations so that we don't, again, accidentally apply the wrong tools to the wrong constructions and get garbage, right? So the whole point to all of this is correct, strict, proper interpretation and use of the terminology. Right? So let me show you a couple of catastrophes that I've seen. It's unfortunate, but if I were to ask, let's say part 2 here, given this, given that line, what is the function? What is a function for which one of the level sets is this line? And I have seen students answer that function. It's not a function. That's an equation. Right? The function, I guess if you're, if you're going to not tell me the domain of the target, and that matters, that's usually a few points. But in the loosest reasonable sense, the function could be thought of as being 2x plus 3y. But not 2x plus 3y equals 6. The left side is a function. The whole thing in green is not a function. It's an equation. And it is important that these are viewed as different, because that specifically is the equation representing a level set of the function, right? And if the question asks, give me a function, you've got to give me a function. Does that make sense? Okay, and I know it comes off as fussy, but it's very important fussy. This is a fussiness that will keep your bridges from falling down. It's a big deal. Yes?
So for that question, you could just say 2x plus 3y is the function?
The way I phrase these typically, keep in mind a function's a trio, and so I want to see domain, target, and formula. Yeah, absolutely. Yeah. Right, and that's another thing. You got to think through, wait a minute, why is a domain 2-dimensional, not 1-dimensional, and stuff like that? Yeah. Here's another one that I see, and again, this is, Man, it's a rough one. But I will see students write down pretty much the right answer, but then say equals 6 at the end. Oh, so close. That's a problem. The function, what has been written down here, makes it look like the student is saying that g of x, y is 6, and that is not the formula for this function. That's a value that the function achieves on the line in question, but again, that's not what the question asked for. What we asked for is what is the function, which if I were to make a level set of it, would give me the line. You can't put the equals 6 on the end here. That makes it wrong. So again, fussy, but again, important fussy. Okay, all right, so we're out of time. We will draw the line right here and see y'all on Friday. Have a good one.